marketplace kind of like Amazon, where you can buy and sell goods, with the main difference being that you don't have to follow any laws and you can do it anonymously. Not following the law is a good way to make a lot of money, but you take on the added risk of going to prison. And Ross Ulbricht saw the downside of that risk when the FBI seized the Silk Road in 2013 and put him in jail for life. But despite Donald Trump saying that drug dealers should get the death penalty, he gave Ross Ulbricht a full unconditional pardon yesterday. In today's video, we'll look at the death penalty. He gave Ross Ulbricht a full unconditional pardon yesterday. In today's video, we'll look at the crazy story and interesting technical details behind the Silk Road. It is January 22nd, 2025, and you're watching The Code Report. Before we get into the Silk Road story, we first need to get one thing perfectly clear.
Drugs are bad. You shouldn't do drugs. If you do them, you're bad. Because drugs are bad, okay?
Because it followed no laws and did all transactions anonymously through Bitcoin, people used it primarily as a marketplace to trade mind-altering substances. Ulbricht was an advocate for individual liberty and a true enemy of the state who not only operated for profit, but to send a message. But the website did prohibit items that caused harm, like weapons of mass destruction or things that would harm children. The website launched in February 2011. Then a few months later in June, Gawker published an article about the site, which dramatically increased its traffic, but also drew the attention of law enforcement. Throughout its 2.5 years of operation, over 100,000 buyers participated, generating $183 million in sales volume, with $13 million of that being commissions going to Ulbricht, all conducted in this relatively unknown cryptocurrency called Bitcoin, which was valued at about $10 per coin at the time. Things were going great, but there was all kinds of drama going on behind the scenes, and there were even allegations that Dread Pirate Roberts tried to hire hitmen to take care of his enemies, although Ulbricht was never convicted of these alleged crimes. When you look into it, the story is very complicated, and it looks more like an FBI informant tried to set him up, and one of the feds on the Silk Road case even went to prison for corruption. The bigger problem is that he was making a bunch of operational security mistakes that allowed law enforcement to find him. To understand these mistakes, you first need to know how to operate an illicit website on the dark web. The Silk Road website itself was nothing special and is believed to use the LAMP stack, which includes PHP and MySQL, with a web server like Apache running on Linux. Now, normally to host a website, you point a URL to an IP address, but that's not going to work if you want your service to be anonymous and untraceable. And that's where the Tor browser and Onion services come in. The Silk Road could only be viewed in the Tor browser because it was hosted via Onion services and only accessible through the Tor network, distinguished by a .onion domain, which provides an overlay network on top of TCP/IP to hide the service's location and provide end-to-end encryption and authentication. Communication between the client and server is broken up between relays in the network, making it virtually impossible to know the identity and location of the client or server. If your website needs this feature, you can easily accomplish this by installing the Tor package on your server, then create a Tor config file that points to your service. Restart Tor, and that'll automatically generate your Onion address. And now you can access your website on the Tor network anonymously. But pretty cool, and Ross would have gotten away with it if he were a little more careful. Like in the early days of the Silk Road, he accidentally used his real name in an online forum post promoting the site, and he even used Stack Overflow just like the rest of us. He also reused the username Altoid, which was eventually tied to his Gmail account. In addition, Bitcoin itself is a public ledger by design, and only pseudo-anonymous. That's why modern criminals and privacy advocates prefer coins like Monero. But the silliest mistake is that the real IP address for the server was accidentally leaked in the website's CAPTCHA. That led the feds to a server in Reykjavik, Iceland, but some developers find this highly sus because there's really no error that could leak an IP address in a CAPTCHA. And the conspiracy theory is that the FBI used some secret high-tech tool that they don't want anybody to know about. But at this point, they had enough evidence and arrested him on October 1st, 2013, at a public library in San Francisco. They distracted him and were able to arrest him without him closing the laptop while he was logged in to the Silk Road's admin panel. And get this, they found a wallet with 144,000 bitcoins on that laptop. At the time, that was only worth a measly $28 million, but at today's prices would be worth $14 billion. At this point, the feds had a slam dunk case, and eventually he received 2 life sentences without the possibility of parole. Now, not many people argue that what he did was good and he shouldn't go to prison, but many people argue that his punishment was too harsh. Murderers and violent criminals often get far lighter sentences, and Trump chose to pardon him because he believes he was unfairly burned at the stake, not for causing harm, but for being a heretic to the deep state. It's a highly controversial pardon, and people have mixed feelings, but one thing's for sure, the Joe Rogan-Ross Ulbricht interview is going to be an absolute banger. This has been The Code Report, thanks for watching, and I will see you in the next one.
Assembly. a family of programming languages that communicate directly with the CPU and whose syntax may look stupidly convoluted if you've never looked at it before. As someone who really likes programming in C, I've always wanted to learn assembly, but I never knew where to start. Until a few weeks ago when I was scrolling through Reddit and I found this book called Programming from the Ground Up, which is aimed at newcomers who want to get started with programming. And yes, I mean programming, not just assembly. The author doesn't fuck around at all. He quite literally says, if you want to learn programming, don't be a bitch and start with assembly. So I decided to give the book a try, learn a few things here and there, and make a video about it because it's been 100 years since the last time I uploaded something and I don't want YouTube to shadow ban me. Now take everything I'm gonna say here with a grain of salt, because I'm just a dude making a YouTube video and not a college professor. Before I get into the actual details of assembly code, there are a few things I need to point out, so bear with me for a few seconds. As I mentioned at the start of the video, assembly is not exactly one programming language. It's more like a family of languages. Assembly communicates directly with your CPU, so depending on the CPU's architecture, the way you communicate with it will vary. Now the book I'm reading was written back in 2003. That's more than 20 years ago, so naturally, it focuses on writing assembly for an x86 32-bit architecture using the old AT&T syntax. Now, don't worry about the technicalities of it. Even though various assembly languages may look very different from one another, they all follow, at least as far as I'm aware, the same basic principles. Keep in mind that I'll be simplifying a lot of things because I don't want this video to be too long. The thing on the left is your computer's CPU. The thing on the right is your memory. Your memory is divided into bytes, and each byte has its own unique address. Your CPU uses these addresses to find all the information it needs to operate. In a 32-bit architecture, addresses are 32 bits wide. On a basic level, your computer can only perform simple operations, usually add, subtract, compare, multiply, and things like that. So in order to run a program, the CPU checks whatever is in the memory and it performs operations on it. To accomplish this, the CPU uses registers to pass data from the memory to itself and back. To better illustrate the whole process, let's use the following assembly program as an example. The main part of this program is this line, start. In assembly, this is called a label. Since assembly is very low level, it involves a lot of jumping back and forth different memory addresses. To make this easier, we use labels to refer to these memory addresses, so we don't have to memorize them. You can see that the label is defined as global. This just means that this label is exposed to the linker so we can use it as an entry point for the program. And if that sounds confusing, you can think of it as the main function in C. Then we get three instructions. We move the number 1 to the EAX register, we move the number 0 to the EBX register, and the final line initiates a system call to the Linux operating system. The $sign in front of the number just means that we are moving a constant value to the register. The instruction MOVEL is used to move data from one place to another. The L at the end of the instruction stands for long, which means that we're moving 4 bytes. You can think of system calls as asking the operating system for help. You interrupt the execution of your program and the operating system takes care of the rest. The INT here stands for interrupt. They allow you to do things such as opening files, reading and writing data, forking, and in this case, exiting the program. Different system calls require you to pass different data in the registers before calling them. This is sort of like passing parameters to a function in a higher level language. As you can see in this table, for an x86 32-bit processor, the system call 1 will exit the program. In order to call it, we need to assign the number 1 to EAX and put the status code in EBX. So this can sort of be translated to the following C program. See? Very simple. Learning programming from books is fun and everything, but sometimes it gets too boring. You need to add some spice to your programming journey. That's why today's sponsor, But.dev, is a great opportunity for you. But.dev is essentially gamifying the learning process. The main focus of it is to teach you backend development from start to finish in Python and Go programming languages. And as we all know, backend is the goated part of web development. Through a hands-on approach, you can learn topics such as data structures and algorithms, functional programming, HTTP servers and clients, Git, Docker, and more stuff like that. Each course is split into digestible small lessons so you can reach your goals by just being consistent. It also offers a variety of coding projects so you can expand your GitHub portfolio with actual finished stuff. You gotta write lots of code to learn how to code, right? But what about the gamifying part? Well, besides the fact that it's got a cool RPG theme going on, it also includes XP, levels, achievements, quests, leaderboards, and all the other things you can think of. There are even bi-monthly boss fights where the community rallies together to gain bonus XP for each lesson completed during the event. If you want to try it by yourself, go to but.dev and use my code MULT to get 20% off your entire first year if you choose the annual plan. With that being said, thanks to but.dev for sponsoring this video. Now here comes the part that every programmer does when learning a new language. Writing
で二人でいたい夢の中に君がいて全てが美しい瞬間を生きて手をつないで星を数えればこの愛が永遠変わらないこのまま世界が終わればいいって君と一緒にいると思うんだ逃げた星空に君が広がり手を伸ばせば全て叶った夢のようにそんな今があったなんて甘ったるくて忘れられない二人の思い出星のように輝きこの瞬間を心に刻んで甘酸っぱい恋が風に乗って時を止めて永遠に続くこのまま世界が終わればいいって君と一緒にいると思うんだ見えてた星空に君が広がり手を伸ばせば全て叶った夢のようにそんな今があったなんて甘ったるくて忘れられないこの瞬間をずっと感じていたい君の隣で全てを知りたい星空の下二人で奏でる甘ってて切ない愛の歌夜空に輝く星たちを見つめ思い出に浸るこの瞬間君といた時間がまるで幻手を伸ばしても届かない心の奥静かにざわめく夢の中で君と踊り明かす目を閉じてもう一度感じてでも現実は冷たいまま夢から覚めることができない君のぬくもりが消えないようにこの愛を信じてさまよう夜現実に戻る勇気がない夢の中で君と生きていたい
Corresponding to the get HTTP verb. Export async function get. The function name matching an HTTP verb. Within this folder, we create a new file. This time, the file name is route.ts. Again, this is a Next.js convention we must follow. Within the file, we define and export a function corresponding to the get HTTP verb. Export async function get. The function name matching an HTTP verb is another convention we must follow. For our simple API, we're going to respond with plain text. We will be using the standard JavaScript response object to respond to an incoming request. So we return a new response with the text, "Hello world." And believe it or not, we have created our first route handler with Next.js. With the dev server running, in the browser, navigate to localhost 3000/hello. We see the same plain text as response, "Hello world." Our route handler is working as expected. This is pretty much the gist of route handlers. Create a route.ts file that exports HTTP verbs as functions. In our example, a GET request to /hello results in the GET handler being executed and responding with "Hello world" plain text. Now there are 2 points to make note of. First, similar to page routes, route handlers can be organized in folders and nested within subfolders. This allows for cleaner organization and easier management of routes. For example, you could create a dashboard folder within the app folder, and then add a route handler within the folder. Copy the route.ts file and paste it within the dashboard folder. Change the text to dashboard data. You can then create a subfolder within the dashboard folder for users, and create another route handler. Copy and paste route.ts and change the text to user data. In the browser, you can navigate to /dashboard, which returns dashboard data, and /dashboard/users, which returns user data. Second point, be mindful of potential conflicts between page routes and route handlers. For example, if you have a route profile with page.tsx with a React component that returns a simple h1 tag profile page and another file named route.ts within the same profile folder with a handler function profile API data. This route.ts will handle the request by default. So if we navigate to /profile, you will see the text profile API data. To avoid this conflict between page.tsx and route.ts and have both of them working, you can move the route handler to an API subdirectory. So within the profile folder, create API folder and move route.ts within the folder. Now, if I refresh, you can see the profile page is available at /profile, and the API for the same is available at /profile/API. Very important to keep this in mind. To summarize, route handlers allow you to create custom request handlers for a given route. They are defined in a route.js or TS file inside the app directory. A route.ts file at the same route segment level as page.tsx will result in a conflict and the page will not be served. Alright, if you now have an idea of how route handlers work, over the next few videos, let me show you simple examples of how to handle get, post, patch, and delete requests with route handlers in Next.js. Thank you for watching, and I'll see you in the next one. In the previous video, we learned how to create a basic route handler. In this video, and over the next few videos, let's understand more about working with route handlers. In this video, let's focus on handling a GET request. Before we start, I want to mention that for this topic on route handlers, we will not be focusing on the UI. Instead, we will be relying on Thunder Client, which is a REST API client for VS Code. It will help us make the necessary requests to test our route handlers. Please pause the video and install this VS Code extension. If you have it installed, let's proceed. For our examples, we are not going to set up a database, as that would become a distraction in itself. We're going to keep it very simple and maintain the data in memory, which of course implies the data is lost when we restart the application or refresh the page. But that shouldn't matter, as our focus is primarily on creating route handlers. Now, to respond to a GET request, we need some data to begin with. Within the app folder, I'm going to create a new folder called comments. Within the folder, I'm going to create a new file called data.ts. The file name is not a Next.js convention. Within the file, I'm going to copy and paste an array of 3 comments. Each comment has an ID property and a text property. We have IDs 1, 2, and 3, and the text, this is the first comment, second comment, and third comment. Really simple. You can think of these as user comments on a YouTube video. With our data in place, let's proceed to create our route handler. Within the same comments folder, create a new file, route.ts. Within the file, we define and export a getHandler function. Now, this is something we will be repeating a lot, so I have created a snippet out of it. I'm using an app called Pieces, which has a VS Code extension, Pieces Explorer. Here, you can see a list of 3 snippets that I regularly use for the Next.js videos. Route handler is one we will be using a lot in the upcoming videos. With the cursor in place, I can right-click on route handler and select Insert Snippet. And without spending too much time, we have our get route handler in an instant. This function will return a new response object of the comments array in the JSON format. Let's import the comments array from /data and update the return statement response.json comments. This completes our route handler to make a GET request. To test this handler, open Thunder Client and click on New Request. The HTTP verb will be GET, but the URL we change to http localhost 3000/comments. We can leave everything else as it is. When I click on the Send button, we have status 200 OK, and we get back our array of 3 comments. The GET handler is working as expected. At the moment, we are using Thunder Client to fetch the comments, but in a real-world application, the UI would make a request to fetch the comments on page load or on click of a button. But the bottom line is that we are able to define route handlers with Next.js. In the next video, let's understand how to handle a post request. Thank you for watching. Please do consider subscribing to the channel, and I'll see you in the next one. In the previous video, we learned how to handle a GET request. In this video, let's learn how to handle a post request. We're going to leave the GET request tab from the previous video untouched and create a new request instead. we select the HTTP verb as host, and the URL is http localhost 3000/comments, the same as the GET request. Next, we need to specify a new comment object that needs to be added to the comments array. For that, in the body tab under JSON, we specify an object, text. The value is new comment. We don't specify the ID as it will be generated in the handler function. If I now click on send, we get back an error 405 method not allowed. Let's go back to our API route and add a function to handle this post request. In the same route.ts file in the comments folder, I'm going to define and export a new function. Let's insert the route handler snippet from pieces extension and rename to post. It's important we match the function name with the HTTP method we want to handle. Now, every route handler function receives the standard web request object as a parameter. From this request object, we're going to extract the JSON body specified as part of the request. For that, we call request.json and await it. This returns the object specified in Thunder client, which we're going to store in a constant called comment. Next, we can create a new comment object. The ID is set to the comments array length plus 1, and the text is the text from the request body comment object. So comment.text. We then push this new comment into the comments array. Finally, we return a response object. If we were to respond with response.json, the status would remain 200. For a post request, a 201 status of resource creation is more appropriate. So our response statement is slightly different. Return new response, and as the first argument, we specify the new comment as JSON. So JSON.stringify, new comment, and for the second argument, we set the headers with content type to application/JSON and status code 201. This indicates a new resource has been created. If we now restart the dev server with npm run dev, hit the GET request first, we get back the 3 comments. Hit the send button for the post request, we see 201 created status, new comment, which is our text, and ID is comments length plus 1, which is now 4. If I switch tabs and make a GET request again, we now see all 4 comments being returned. This is pretty much how we handle post requests. Define a post handler in the route.ts file, make use of the request parameter to access the request body, and send an appropriate response. If you've understood so far, join me in the next video where we will learn about dynamic route handlers. Thank you for watching, and see you in the next one. In the previous 2 videos, we learned how to create route handlers for GET and POST requests. The next step is to understand how to handle patch and delete requests. Patch or delete request, though, is slightly different in the sense that you need to specify the ID of the comment you're updating or deleting. While /comments route will handle both GET and POST requests, for a patch or delete request, our endpoint will be /comments/ID, where ID is the dynamic segment. It can be 1, 2, 3, or any valid ID from our comments array. So in this video, let's see how to create a dynamic API route, which will return a single comment based on the ID. We will then use our learnings from this video to handle patch and delete requests in the next 2 videos. Alright, so we need to create a route handler for /comments/ID. Let me tell you that dynamic route handlers work similar to dynamic page routes. Within the comments folder, we create a new folder named ID wrapped in square brackets. Inside this folder, we create a route.ts file. Within this file, we define a get handler function. Once again, we will make use of pieces extension to insert the saved snippet. From this function, we need to return a single comment whose ID matches the ID route parameter. Let's first import the comments array at the top. Next, we need to access the route parameter. The handler function receives 2 parameters. The first one is the request object, which we looked at in the previous video. However, we are interested in the second parameter, the context. Currently, the only value of context is params, which is an object containing the dynamic route parameters for the current route. So from context, we destructure params. Params is an object that contains the ID route parameter, which is of type string. ID corresponds to the ID folder name. Using this ID, we can now find the individual comment. So const comment is equal to comments array dot find, and as the callback function, we find the comment whose ID is equal to the integer value, so parseInt of params.id. Params ID is a string value, and we need to convert it to integer to compare it with the comment ID. Once we have the comment, we respond with it in JSON format. So return response.json comment. Since we are not using the request parameter, we can prefix it with an underscore. Now, Now I will switch over to the Thunder Client tab where we were making the GET request. To the URL, I'm going to append /1, with 1 being the comment ID. If I hit send, you can see the status is 200 OK, and the comment with ID equal to 1 is returned. Changing the URL to /2, we get back the second comment. Similarly, /3, we get back the third comment. So based on the comment ID we pass in the URL, we get back the appropriate comment. We have only 3 comments to work with, but in a practical application, you're likely to have thousands of rows in your database. The logic to fetch the individual record, however, remains the same. Alright, now that we have a good understanding of how to create dynamic route handlers, in the next video, let's see how to handle a patch request to update an individual comment. Please do leave a like if you're enjoying the videos, and I'll see you in the next one. In this video, let's learn how to handle patch requests. A patch request applies partial modifications to a resource. In our case, since we have just the one property, text, updating the comment is quite straightforward. Let's begin by understanding what a patch request looks like in Thunder Client. I'm going to first change the HTTP verb from get to patch. The URL remains the same as we will be updating the comment with ID 3. Under the body tab in the JSON section, I'm going to add an object with the text property set to a different string. Updated comment. We don't specify the ID as it is already part of the URL. If I now hit the send button, we see status 405 method not allowed. Let's go back to our dynamic route handler and add a function to handle this patch request. In route.ts within the ID folder, I'm going to use pieces to insert a route handler function. The function is an async function called patch. The function receives request and context as parameters. So request of type request, and context is the same as the get request handler. It's an object with params, and params contains our ID, which corresponds to the folder name. Within the function, we extract the JSON body that is sent as part of the request. So const body is equal to await request.json. We then destructure text from body. This property right here. Next, we find the comment that we need to update. We can use either array.find or findIndex. I am going to use findIndex as we will use the same method for delete as well in the next video. So const index is equal to comments.findIndex, and for the callback, find the comment whose ID is equal to parseInt params.id. Once we have found the index for the comment, we update the text property on that comment. So comments of index, which is the comment we want, dot text is equal to the text we have extracted from the request. Finally, we return a new response with the updated comment as JSON. So return response.json comments of index. If we now go back to Thunder Client and hit the send button, we see status 200 OK and the updated comment as the response. ID 3 text updated comment. You can also verify the entire list by restarting the server. So npm run dev, make a get request to /comments. We see ID 1, 2, and 3, the text being the original text. Send a patch request to update the third comment text. Send a get request again, and we see ID 3 has the updated text. This is essentially how we handle patch requests in route handlers. In the next video, let's see how to handle delete requests. Thank you for watching, and I'll see you in the next one. In this video, let's learn how to handle delete requests. A delete request deletes a specified resource. In our case, we delete a comment by ID. Let's begin by understanding what a delete request looks like in Thunder Client. I'm going to first change the HTTP verb from patch to delete. The URL remains the same as we still need the comment ID to be part of the URL. We will be deleting the comment with ID 3. We can clear the body JSON to avoid any confusion, as it is not necessary for a delete request. If I hit the send button, we see status 405 method not allowed. Let's go back to our route handler and add a function to handle this delete request. In route.ts within the ID folder, once again, I'm going to use pieces to quickly insert a route handler function. Function is an async function called delete. The function receives request and context as parameters. We're going to copy paste the same from the patch function. Within the function body, we find the index of the comment object that needs to be deleted using array.findIndex method. We can copy this logic from the patch function. So find the index of the comment whose ID matches params.id. Next, we store the comment at the given index to return it later. Const deleted comment is equal to comments of index. We then use array.splice to remove the item at the given index. So comments.splice at position, index, and the delete count is 1. Finally, we return a new response with the deleted comment as JSON. So return response.json deleted comment. If we now restart the dev server, go back to Thunder client and hit the send button, we see status 200 and the deleted comment as the response. This is the comment with ID 3. If I switch tabs to make a GET request, we notice that the comment with ID equal to 3 is no longer part of the array. This is how we handle delete requests in route handlers. Alright, now that we understand how to handle get, post, patch, and delete requests, let's take a look at a few more related topics in the upcoming videos. Thank you for watching. Please leave a like if you're enjoying the videos and make sure to subscribe to the channel. I'll see you in the next one. Welcome back, everyone. In this video, we will learn how to work with URL query parameters in a route handler. In our data.ts file, we have an array of 3 comments. Let's consider an example where we want to filter this array based on a specific query. For instance, if you navigate to localhost 3000/comments, we see the full list of comments, but if you navigate to /comments, query is equal to first, you expect to see only those comments containing the word first. In this case, comment with ID set to 1. How do we achieve this with route handlers? Let's head back to VS Code and find out. To handle query parameters effectively, we need the request parameter. Let's add it to our getHandler, which currently responds with our list of comments. Up until now, we've been defining the request type as the standard request API. However, in the context of Next.js, the type we are actually dealing with is next request, which we can import from next/server. The next request object provides convenient methods for managing query parameters with ease. Let's update our code to reflect that. We first use request.nextURL.searchParams to access all the query parameters. Let's store it in a constant called searchParams. We then use the get method to retrieve the value of the individual parameter, which in our case is query. So const query is equal to searchParams.get. Parameter name is query. Depending on whether the query parameter is present, we filter the comments array to include only those comments where the text includes the search term. So const filtered comments is equal to query. If it is present, we're going to filter the comments array such that we select only those comments whose comment text includes the query. If no parameter is present, we default to returning all comments. Finally, we return the filtered comments in a JSON response. If we now head back to the browser and refresh the URL localhost 3000/comments, query is equal to first, we see only the first comment. Changing the query to IR will display the first and the third comments, which contain the search text IR. If we remove the query parameter, we get back the full list of 3 comments. This is how you work with query parameters in route handlers. Query parameters are often optional, but they are incredibly useful for implementing search, sort, and pagination functionalities for your data. Alright, thank you for watching. We'll see you in the next one. Welcome back, everyone. In this video, we're going to learn about handling redirects in route handlers. Remember, in an earlier video, we implemented a dynamic route handler to return an individual comment by its ID. When we enter URLs like /comments/1 or /comments/2 in the browser, we see the corresponding comments. However, when we try /comments/4, we encounter an error because our current logic doesn't handle IDs that are not present in the comments array. Let's improve this by redirecting to the comments listing page if the request ID is not found. For redirection, we will make use of the redirect function from Next Navigation. So in the route.ts file within the ID folder, at the top, import redirect from next/navigation. In our route handler function, we will add a simple check right at the start. We will verify if the entered ID is greater than the number of comments we have. If it is, we will perform a redirect to the comments listing page. If parseInt columns.id is greater than the comments array.length, we redirect to /comments, which is the listing page. I have chosen this approach for its simplicity, assuming that the IDs in our comments array are sequential. You can of course opt for an array method to handle this logic. Now let's see this in action. If you go back to the browser and navigate to /comments/3, you will see the third comment. But if you try to navigate to /comments/4, instead of an error, you will be redirected to /comments, and this offers a much better user experience. Also, do notice the request status when you try /comments/4 again. It shows a 307 status code indicating a temporary redirect. What we have here is just one possible use case for redirection. I want to make sure you're aware of the concept, so apply it as needed in your project. Thank you for watching. Please consider subscribing to the channel, and I'll see you in the next one. Welcome back, everyone. In this video, we will learn about dealing with headers in route handlers. Let's start by understanding headers in general. HTTP headers represent the metadata associated with an API request and response. This metadata can be classified into two categories. First, we have request headers. These are sent by the client, such as a web browser, to the server. They contain essential information about the request, which helps the server understand and process it correctly. For example, we have the user agent header, which identifies the browser and operating system to the server. It is often used for browser-specific content rendering and analytics. We have the accept header, which indicates the content types like text, video, or image formats that the client can process. It enables the server to deliver the resource in a format suitable for the client. Another common request header is the authorization header used by the client to authenticate itself to the server. It carries credentials allowing controlled access to resources. Second, we have response headers. These are sent back from the server to the client. They provide information about the server and the data being sent in the response. An example is the content type header, which indicates the media type of the response. It tells the client what the data type of the returned content is, such as text/HTML for HTML documents, or application JSON for JSON data, etc. When defining route handlers in Next.js, it is important to understand how to read request headers and send back response headers. Let's head over to VS Code to understand this. Let's make use of the profile API route we had created earlier. I'm going to create a new request with the Thunder client extension. The URL is http localhost 3000/profile/API. By default, the request has two headers, accept and user agent. Let's add a third one, authorization. We can set the value to a bearer token. Bearer 12345. Now, how do we read these headers in our route handler? Well, there are two ways. The first one is using the request parameter. At the top, import type next request from next/server and specify the parameter with its type. Within the handler function, we use the headers web API to extract the request headers. So const request headers is equal to new headers, and we pass in request.headers. In the next line, we can use the get method on request headers and log the authorization header to the console. Request headers.get, the name of the header is authorization. If we go back to Thunder client and resend the request from Thunder client, in the terminal, we should see our bearer token, bearer 12345. While this first approach works completely fine, you can also choose choose to use the headers function that Next.js provides. At the top, import headers from next/headers. And then within the function body, we invoke the headers function and store the result in a constant. We then access the authorization header using the get method and log it to the console. Headerlist.get authorization. Open the terminal, switch to Thunder Client tab, and send the request. We see the bearer token logged twice in the terminal. Let me show you an example. If you were to access /profile/API route in the browser, we see the text profile API data. If we take a look at the network tab, the response header has content type text/plain. So if we were to wrap this response string in an h1 tag and refresh, we see the same in the browser. However, if we change the content type header to text/HTML, so second argument, headers, which is an object, content type, text/HTML, and refresh the browser, you can see the UI is now different and we have our h1 styled text. The client, which is the browser, renders the content differently based on the response header. But the key takeaway is that to set headers, you need to return a new response with new headers. Using request and response headers, you can apply any logic you want to within the route handler. Alright, thank you for watching, and I'll see you in the next one. In the previous video, we learned how to work with headers in route handlers. In this video, we will learn how to work with cookies in route handlers. Cookies are small pieces of data that a server sends to a user's web browser. The browser may store the cookie and send it back to the same server with later requests. Cookies are mainly used for three purposes: session management, like logins and shopping carts; personalization, like user preferences and themes; and tracking, like recording and analyzing user behavior. You can learn more about cookies on NDN, but with this introduction in mind, let's return to VS Code and understand how to use them inside a Next.js route handler. Just like in the previous video, our primary goal is to learn how to set and get cookies inside of a route handler. Now there are two approaches to both setting and getting cookies. To set a cookie, the first option is to return a new response using the set cookie header. So after content type, set cookie, key is going to be theme, and value is going to be dark. If we now go back to Thunder Client and switch to the cookies section, you can see we have no cookies available. After making the GET request, we see the theme cookie being set. Theme is the name, dark is the value. Now to read this cookie in our route handler, we can make use of the request parameter. So const theme is equal to request.cookies.get, and the cookie name is theme. We can then log to the console theme. Back in Thunder Client, send the request, and in the terminal, we should see the cookie name value pair being logged. Name is theme, value is dark. Now this is the first approach to set and get cookies in a route handler, using the set cookie header and the request object. The second option is to set and get cookies using the cookies function provided by Next.js. Let's import it at the top. Import headers, comma, cookies from next headers. Now, to set a cookie, we can invoke cookies, which is a function, dot set, let's call this results per page, and the value is 20. Back in Thunder Client, send a request, and we should see the new cookie results per page with the value of 20. To read this cookie, we can use cookies, which is a function, dot get, and we specify results per page. Go back to Thunder Client, send the request, and in the terminal, we should see the value 20 with the path of homepage. Now, apart from set and get, the cookies function supports other methods like has, delete, and so on. Please refer to the documentation for more information. right, that covers working with cookies in route handlers. Thank you for watching. Please do consider subscribing to the channel, and I'll see you in the next one. Welcome back, everyone. In this final detail about route handlers, we will explore the caching behavior. Route handlers are cached by default when using the get method with a response object in Next.js. Let's dive into this in VS Code. Within the app folder, we will create a new folder named time. Inside this folder, let's create a new route.ts file. Here, I'll use pieces snippets to add a get handler. So pieces explorer, insert snippet. We will update the response to JSON format and return the current time. So return response.json time new date dot to locale time string. In the browser, navigating to localhost 3000/time displays the current time in hours, minutes, and seconds. On reloading, the time updates, showing us the latest time when we make a request to our route handler. This is the behavior in development mode. Let's build our application and test it again. In the terminal, execute npm run build, followed by npm run start. Then return to the browser and reload /time. We see the current time, which is 2:10 p.m., 13 seconds. However, if I reload this page, the time doesn't update. Even after multiple reloads, it remains the same. This is the caching behavior I mentioned at the start of this video. Route handlers are cached by default when using the get method with the response object. But this, of course, begs the question, how do we inform Next.js that we don't want the response to be cached? Now we can use what's known as a segment config option with a dynamic mode. At the top of segment config option with a dynamic. Now we can use what's known as a segment config option with a dynamic mode. At the top of route.ts, add export const dynamic is equal to force dynamic. By default, the value of dynamic is auto, which attempts to cache as much as possible. We will set it to force dynamic, ensuring that the handler is executed for each user request. If we now rebuild our application with npm run build and rerun with npm run start or npm start, reload the /time route in the browser, we see the current time to 12:43 p.m. Refresh, and we see the seconds updating. We have successfully opted out of caching. Now, besides the segment config option, there are 3 other ways to opt out of caching for a route handler. These include using the request object with the get method, which is the parameter we have seen so far, employing dynamic functions like headers and cookies, which we previously learned about, and using any HTTP method other than get. In all these 4 scenarios, the response is not cached. I hope caching behavior in route handlers now makes sense to you. Thank you for watching. Please do consider subscribing to the channel, and I'll see you in the next one. Welcome back, everyone. For our final topic on routing in Next.js, we will learn about middleware. Middleware in Next.js is a powerful feature that offers a robust way to intercept and control the flow of requests and responses within your applications. And it does this at a global level, significantly enhancing features like redirection, URL rewrites, authentication, headers and cookies management, and more. Let's go back to VS Code and define a middleware in our application. To create middleware in Next.js, start by adding a middleware.js or .ts file in the source folder. Now, middleware allows us to specify paths where it will be active. And there are 2 main approaches: custom matcher config and conditional statements. We will explore both using redirection as an example. And there are two main approaches: custom matcher config and conditional statements. We will explore both using redirection as an example. Imagine a scenario where navigating to /profile should redirect the user to the home page. Here is how we can achieve this. We start by importing next response, which extends the standard response API, and the type next request. We then define a middleware function, export function middleware, that accepts a next request type request. So request of type next request. This function redirects the user to the home page when /profile is accessed. So return next response dot redirect to the new URL, which is the home page, and the base URL is request.url. The config object, so export const config, specifies a matcher /profile to which this middleware applies to. Now, when you navigate to /profile in the browser, it automatically redirects to the home page, showcasing the matcher config approach. For the second approach, we use conditional statements. We will leave the import statement as it is and comment out the rest of the code. Instead, we write an if condition. So if request dot next URL dot path name is equal to /profile, we return next response dot redirect, and this time let's navigate to /hello to make sure we're using the second approach. Visiting /profile again redirects to the /hello route created a few videos earlier. This shows how conditional statements can control middleware responses based on the This shows how conditional statements can control middleware. Responses based on the request path. Apart from handling redirections, middleware also allows URL rewrites, which is a useful tool for legacy URL support or SEO optimization. By changing redirect to rewrite, navigating to /profile, you can see the URL in the browser stays the same, /profile, but the response content changes. This is the response from /hello route. Lastly, let's explore the use of cookies and headers in middleware. Rewrite, navigate is a useful tool for legacy URL support or SEO. URL rewrites, handling redirections. Middleware also allows URL rewrites, which is a useful tool for legacy URL support or SEO optimization. By changing redirect to rewrite, navigating to /profile, you can see the URL in the browser stays the same, /profile, but the response content changes. This is the response from /. Hello route. Lastly, let's explore the use of cookies and headers in middleware. We will modify our middleware to handle user preferences for themes and add a custom header for all responses. First, we obtain the response object that we will eventually return from our function. So const response is equal to next response, which we have imported, dot next. Then, using the request object, we retrieve the user's theme preference from cookies using request.cookies.get. The name of the cookie is T. If the theme preference is not found, indicating that the user has not set a theme preference yet, we default to a dark theme by setting the response theme cookie to dark. So response.cookies.set. The key is theme and the value is dark. Finally, we ensure that this tailored response is what we send back from our middleware function. Return response. If we now go back to the browser and take a look at cookies in the DevTools, you can see they are empty. If we refresh /profile, you can see the dark theme cookie being set. If we manually overwrite the value to light, assuming it was changed from the UI, and then refresh, you can see the value is not overwritten to dark, and our application remembers the user's preference. Very simple to work with cookies. In middleware, working with headers is also straightforward. Let us set a custom header in the response using response.headers.set. Here, we add a header named custom header with the value custom value. Open the network tab, refresh the page, and for /profile, Under response headers, we see custom header, custom value. Custom headers are useful for passing additional information in responses, which can be leveraged by client-side scripts or for debugging purposes. As you can see, middleware can be effectively used to manipulate both cookies and headers. In summary, middleware in Next.js allows you to effectively control and intercept the request-response cycle, enabling redirects, URL rewrites, and the manipulation of headers and cookies. With that, we complete this first section on routing in Next.js. We've learned a lot, so I want to take a minute to list down all the concepts we have learned. First, we learned how to define routes with pages and layouts. We then learned about dynamic routes and route groups. We followed that with linking and navigation. We then learned how to handle errors in routes. After that, we dived into advanced routing concepts like parallel routes and intercepting routes. We then learned about route handlers, which will help us define RESTful API endpoints. Finally, we learned the role of middleware in routing with Next.js. It took us 44 videos to finish the first section, but I hope you now have a solid understanding of how routing works in Next.js. If you have enjoyed the content so far, please do leave a like and subscribe to the channel. I'll see you in the next section. Welcome back, everyone. In our first section of this series, we dived into the intricacies of routing in Next.js. With that solid foundation, it's now time to move on to the second section, rendering in Next.js. At its core, rendering is a straightforward concept. It's the process of transforming the component code you write into user interfaces. However, choosing the right time and place to do this rendering is vital for building a performant application. You might have come across terms like CSR, SSR, and RSCs and felt a bit confused. Don't stress about it, because this part of our series will explain everything clearly. Before we dive into rendering in Next.js though, let's first understand rendering in React, the library on which Next.js is built. This understanding will help us better grasp how rendering works in Next.js. Finally, I want to mention that we will be covering a lot of different concepts in this section. As you watch the videos, it is normal to find some topics a bit tricky at first. If you don't fully understand something in a video, try watching it again, maybe even a third time. Trust me, going over things more than once can really help you understand them better. Alright, now that we have covered the section introduction, let's explore rendering in React. To fully understand rendering in Next.js, it helps to know about the evolution of React's rendering over the past decade. So in this video and over the next few, let's understand how React has evolved its rendering strategies. If you have been in the development game for a while, you'll remember React being the go-to library for creating single-page applications. In a typical single-page application, when a client makes a request, the server sends a single HTML page to the browser. This HTML page often contains just a simple div tag and a reference to a JavaScript file. Here's an example of the HTML file from Create React App, a tool used to scaffold React apps back in the day. We have an empty div tag and a reference to bundle.js. This JavaScript file contains everything your application needs to run, including the React library itself and your application code. It is downloaded when the HTML file is parsed. The downloaded JavaScript code then generates the HTML on your computer and inserts it into the DOM under the root div element, and you see the user interface in the browser. This process is evident when you see the HTML appear in the DOM inspector, but not in the view source option, which shows the HTML file sent by the server to the browser. This method of rendering, where the component code is transformed into a user interface directly within the browser, is known as client-side rendering. Client-side rendering became the standard for single-page applications with widespread adoption. However, it wasn't long before developers began noticing some inherent drawbacks to this approach. First, generating HTML that mainly contains a single div tag is not optimal for SEO, as it provides little content for search engines to index. Large bundle size and a waterfall of network requests for API responses from deeply nested components may result in meaningful content not being rendered fast enough for a crawler to index it. Second, having the browser handle all the work, such as fetching data, computing the UI, and making the HTML interactive, can slow things down. Users might see a blank screen or a loading spinner while the page loads. This issue tends to worsen over time, as each new feature added to the application increases the size of the JavaScript bundle, prolonging the wait time for users to see the UI. This delay is particularly noticeable for users with slow internet connections. Client-side rendering laid the groundwork for the interactive web applications we're used to today, but to enhance SEO and performance, developers started looking for better solutions. Join me in the next video where we will explore the second rendering technique and understand how it addresses the limitations of client-side rendering. In the previous video, we learned about client-side rendering in React. We also learned the drawbacks of client-side rendering, which include two key challenges. First, its reliance on JavaScript for rendering content on the client side can significantly hurt SEO, as search engines might struggle to index the content properly. Second, the user experience can suffer from slow load times, as the browser has to download, parse, and execute JavaScript before the user sees any meaningful content on the page. To overcome these drawbacks of client-side rendering, modern React frameworks like Gatsby and Next.js pivoted towards server-side solutions. This approach fundamentally changes how content is delivered to the user. When a request comes in, instead of sending a nearly empty HTML file that depends on client-side JavaScript to construct the page, the server takes charge of rendering the full HTML. This fully formed HTML document is then sent directly to the browser. Since the HTML is generated on the server, the browser is able to quickly parse and display it, improving the initial page load time. The server-side approach effectively resolves the issues associated with client-side rendering. First, it significantly improves SEO because search engines can easily index the server-rendered content. Second, users can immediately see the page HTML content instead of a blank screen or loading spinner. However, SSR's approach to immediately improving the visibility of content has its own complexity, particularly when it comes to the page's interactivity. The full interactivity of the page is on hold until the JavaScript bundle comprising React itself, along with your application-specific code, has been completely downloaded and executed by the browser. This important phase, known as hydration, is where the static HTML page initially served by the server is brought to life. During hydration, React takes control in the browser, reconstructing the component tree in memory based on the static HTML that was served. It carefully plans the placement of interactive elements within this tree. Then React proceeds to bind the necessary JavaScript logic to these elements. This involves initializing the application state, attaching event handlers for actions such as clicks and mouse overs, and setting up any other dynamic functionalities required for a fully interactive user experience. Hydration is an essential concept as we move forward, so please make sure you're comfortable with what you've just learned. Diving deeper, server-side solutions can be categorized into two strategies: static site generation, or SSG, and server-side rendering, or SSR. SSG occurs at build time when the application is deployed on the server. This results in pages that are already rendered and ready to serve. It is ideal for content that doesn't change often, like blog posts. SSR, on the other hand, renders pages on demand in response to user requests. It is suitable for personalized content like social media feeds, where the HTML depends on the logged in user. Usually, you'll see the two collectively being referred to as just server-side rendering, or SSR. Server-side rendering was a significant improvement over client-side rendering, providing faster initial page loads and better SEO. However, SSR introduced its own set of challenges. One issue with SSR is that components cannot start rendering and then pause or wait while the data is still being loaded. If a component needs to fetch data from a database or another source like an API, this fetching must be completed before the server can begin rendering the page. This can delay the server's response time to the browser, as the server must finish collecting all necessary data before any part of the page can be sent to the client. A second issue with SSR is that for successful hydration, where React adds interactivity to the server-rendered HTML, the component tree in the browser must exactly match the server-generated component tree. This means that all the JavaScript for the components must be loaded on the client before you can start hydrating any of them. The third issue with SSR is related to hydration itself. React hydrates the component tree in a single pass, meaning once it starts hydrating, it won't stop until it is finished with the entire tree. As a consequence, all components must be hydrated before you can interact with any of them. These three problems of having to load the data for the entire page, load the JavaScript for the entire page, and hydrate the entire page create an all or nothing waterfall problem that spans from the server to the client, where each issue must be resolved before moving on to the next one. This is inefficient if some parts of your application are slower than others, as is often the case in real-world applications. Because of these limitations, the React team introduced a new and improved SSR architecture. Join me in the next video where we will explore that architecture and understand how it addresses the limitations of traditional SSR. Thank you for watching, and I'll see you in the next one. Must be resolved any of them. These three problems of having to load the data for the entire page, load the JavaScript for the entire page, and hydrate the entire page create an all or nothing waterfall problem that spans from the server to the client, where each issue must be resolved before moving on to the next one. This is inefficient if some parts of your application are slower than others, as is often the case in real-world applications. Because of these limitations, the React team introduced a new and improved SSR architecture. Join me in the next video where we will explore that architecture and understand how it addresses the limitations of traditional SSR. Thank you for watching, and I'll see you in the next one. In the previous video, we learned the fundamentals of server-side rendering in React. We also learned the drawbacks of server-side rendering, which include three key challenges. First, data fetching must be completed before the server can begin rendering HTML. Second, the JavaScript required for the components needs to be fully loaded on the client side before the hydration process can start. Third, all components have to be hydrated before they become interactive. These issues contribute to an all or nothing waterfall scenario, resulting in inefficiencies, especially if certain parts of your application are slower than others. To address these performance drawbacks of SSR, React 18 introduced the Suspense SSR architecture. This new architecture allows you to use the Suspense component to unlock two major SSR features, HTML streaming on the server and selective hydration on the client. Let's explore these two features in detail. As we discussed a minute ago, traditionally, SSR has been an all or nothing affair. The server sends the complete HTML, which is then sent to the client. The client displays this HTML, and only after the complete JavaScript bundle is loaded does React proceed to hydrate the entire application to add interactivity. Here is a similar visualization from a user interface perspective. First, you render all HTML. The client eventually receives it. Then you load all the code and hydrate the entire application. However, with React 18, we have a new possibility. By wrapping a part of the page, such as the main content area, within Suspense component, we instruct React it doesn't need to wait for the main section data to be fetched to start streaming the HTML for the rest of the page. React will send a placeholder like a loading spinner instead of the complete component. Once the server is ready with the data for the main section, React sends additional HTML to the ongoing stream, accompanied by an inline script tag containing the minimal JavaScript needed to correctly position that HTML. As a result of this, even before the full React library is loaded on the client side, the HTML for the main section becomes visible to the user. This solves our first problem. You don't have to fetch everything before you can show anything. If a particular section delays the initial HTML, it can be seamlessly integrated into the stream later. This is the essence of how Suspense facilitates server-side HTML streaming. While we can now speed up the initial HTML delivery, we still have another challenge. Until the JavaScript for the main section is loaded, client-side app hydration cannot start. And if the JavaScript bundle for the main section is large, this could significantly delay the process. To mitigate this, code splitting can be used. Code splitting allows you to mark specific code segments as not immediately necessary for loading, signaling your bundler to segregate them into separate script tags. Using React Lazy for code splitting enables you to separate the main section's code from the primary JavaScript bundle. As a result, the JavaScript containing React and the code for the entire application, excluding the main section, can now be downloaded independently by the client without having to wait for the main section's code. This is crucial because by wrapping the main section within suspense, you've indicated to React that it should not prevent the rest of the page from not just streaming, but also from hydrating. This feature, called selective hydration, allows for the hydration of sections as they become available before the rest of the HTML and the JavaScript code are fully downloaded. From the user's perspective, initially they see non-interactive content that streams in as HTML. Then you tell React to hydrate. The JavaScript code for the main section isn't there yet, but it's okay as we can selectively hydrate other components. The main section is hydrated once its code is loaded. Thanks to selective hydration, a heavy piece of JavaScript doesn't prevent the rest of the page from becoming interactive. Moreover, selective hydration offers a solution to a third issue, the necessity to hydrate everything to interact with anything. React begins hydrating as soon as possible, enabling interactions with elements like the header and side navigation with page types. Then you tell React to hydrate. The JavaScript code for the main. This feature, called selective hydration, and without having to wait for the main section's code. This is crucial because by wrapping the main section within suspense, you've indicated to React that it should not prevent the rest of the page from not just streaming, but also from hydrating. This feature, called selective hydration, allows for the hydration of sections as they become available before the rest of the HTML and the JavaScript code are fully downloaded. From the user's perspective, initially they see non-interactive content that streams in as HTML. Then you tell React to hydrate. The JavaScript code for the main section isn't there yet, but it's okay as we can selectively hydrate other components. The main section is hydrated once its code is loaded. Thanks to selective hydration, a heavy piece of JavaScript doesn't prevent the rest of the page from becoming interactive. Moreover, selective hydration offers a solution to a third issue, the necessity to hydrate everything to interact with anything. React begins hydrating as soon as possible, enabling interactions with elements like the header and side navigation without waiting for the main content to be hydrated. This process is managed automatically by React. And in scenarios where multiple components are awaiting hydration, React prioritizes hydration based on user interactions. For instance, if the side nav is about to be hydrated, and you click on the main content area, React will synchronously hydrate the clicked component during the capture phase of the click event. This ensures the component is ready to respond immediately to user interactions. Side nav is hydrated later on. The three significant drawbacks of traditional SSR have all been addressed by the new Suspense SSR architecture. Despite these improvements in SSR, few challenges still remain. First, even though JavaScript code is streamed to the browser asynchronously, eventually the entire code for a web page must be downloaded by the user. As applications add more features, the amount of code users need to download also grows. This leads to an important question. Should users really have to download so much data? Second, the current approach requires that all React components undergo hydration on the client side, irrespective of their actual need for interactivity. This process can inefficiently spend resources and extend the loading times and time to interactivity for users, as their devices need to process and render components that might not even require client-side interaction. This leads to another question. Should all components be hydrated, even those that don't need interactivity? Third, in spite of servers' superior capacity for handling intensive processing tasks, the bulk of JavaScript execution still takes place on the user's device. This can slow down the performance, especially on devices that are not very powerful. This leads to another important question. Should so much of the work be done on the user's device? These issues highlight the need for a better way to build faster applications that improve upon traditional rendering techniques while overcoming their limitations. Let's take a look at what the solution is in the next video. Thank you for watching. Please consider subscribing to the channel, and I'll see you in the next one. Welcome back, everyone. As we have progressed through this section, we have seen React's rendering strategies evolve from client-side rendering to server-side rendering, and then to Suspense for server-side rendering. Each step introduced its own set of improvements and naturally its own challenges. Suspense for SSR brought us closer to a seamless rendering experience, but we still faced challenges such as increased bundle sizes leading to excessive downloads for users, unnecessary hydration delaying interactivity, and extensive client-side processing that could result in poor performance. To address these challenges, simply taking an incremental step is not enough. We need a significant leap towards a more powerful solution. And that brings us to React Server Components. React Server Components represent a new architecture designed by the React team. This approach aims to leverage the strengths of both server and client environments, optimizing for efficiency, load times, and interactivity. The architecture introduces a dual component model, differentiating between client components and server components. This distinction is not based on the functionality of the components, but rather on where they execute and the specific environments they are designed to interact with. Let's take a closer look at these two types. Client components are the familiar React components we've been using and talking about in the previous rendering techniques. They are typically rendered on the client side, but they can also be rendered to HTML once on the server, allowing users to immediately see the page's HTML content rather than a blank screen. The idea of client components rendering on the server might seem confusing, but it is helpful to view them as components that primarily run on the client, but can and should also be executed once on the server as an optimization strategy. Client components have access to the client environment, such as the browser, allowing them to use state, effects, and event listeners to handle interactivity, and also access browser-exclusive APIs like geolocation or local storage, allowing you to build UI for specific use cases, just as we've done all these years before the introduction of the RSC architecture. In fact, the term client component doesn't signify anything new. It simply helps differentiate these components from the newly introduced server components. Server components, on the other hand, represent a new type of React component specifically designed to operate exclusively on the server. And unlike client components, their code stays on the server and is never downloaded to the client. This design choice offers multiple benefits to React applications. Let's take a closer look at some of the benefits. First, in terms of bundle sizes, server components do not send code to the client, allowing large dependencies to remain server-side. This benefits users with slower internet connections or less capable devices by eliminating the need to download, parse, and execute JavaScript for these components. Additionally, it removes the hydration step, speeding up app loading and interaction. Second, by having direct access to server-side resources like databases or file systems, server components enable efficient data fetching and rendering without needing additional client-side processing. Leveraging the server's computational power and proximity to data sources, they manage compute-intensive rendering tasks and send only interactive pieces of code to the client. Third, server components' exclusive server-side execution enhances security by keeping sensitive data and logic, including tokens and API keys, away from the client side. Fourth, server components enhance data fetching efficiency. Typically, when fetching data on the client side using useEffect, a child component cannot begin loading its data until the parent component has finished loading its own. This sequential fetching of data often leads to poor performance. The main issue is not the round trips themselves, but that these round trips are made from the client to the server. Server components enable applications to shift these sequential round trips to the server side. By moving this logic to the server, request latency is reduced and overall performance is improved, eliminating client-side waterfalls. Fifth, rendering on the server enables caching of the results, which can be reused in subsequent requests and across different users. This approach can significantly improve performance and reduce costs by minimizing the amount of rendering and data fetching required for each request. Sixth, initial page load and first contentful paint are significantly improved with server components. By generating HTML on the server, pages become immediately visible to users without the delay of downloading, parsing, and executing JavaScript. Seventh, regarding search engine optimization, the server-rendered HTML is fully accessible to search engine bots, enhancing the indexability of your pages. Lastly, there is streaming. Server components allow the rendering process to be divided into manageable chunks, which are then streamed to the client as soon as they are ready. This approach allows users to start seeing parts of their page earlier, eliminating the need to wait for the entire page to finish rendering on the server. With RSC architecture, server components take charge of data fetching and static rendering, while client components are tasked with rendering the interactive elements of the application. The bottom line is that the RSC architecture enables React applications to leverage the best aspects of both server and client rendering, all while using a single language, a single framework, and a cohesive set of APIs. React server components improve upon traditional rendering techniques while also overcoming their limitations. Now we have covered quite a bit, so let me simplify it with the key takeaways. React Server Components introduce a new way of building React apps by separating components into two types, server components and client components. Server components run only on the server, accessing data and preparing content without being sent to the browser, which makes the app faster for users because less information needs to download. They can't manage clicks or interactivity directly. Client components, on the other hand, work in the user's browser and handle all the interactive parts of the app like clicking and typing. They can also be rendered on the server for a fast initial load of the site. The setup helps make websites faster, more secure, and easier for everyone to use, no matter where they are or what device they're using. Now you might be wondering, this deep dive into the evolution of rendering in React is great, Vishwas, but how exactly does it help understand rendering in Next.js? What is the connection? Well, the connection is quite straightforward. The app router in Next.js is built around the RC architecture, meaning all the features and benefits we have discussed are already baked into the latest what two types. So let all and as soon as they are ready. This approach allows users to start seeing parts of their page earlier, eliminating the need to wait for the entire page to finish rendering on the server. With RC architecture, server components take charge of data fetching and static rendering, while client components are tasked with rendering the interactive elements of the application. The bottom line is that the RC architecture enables React applications to leverage the best aspects of both server and client rendering, all while using a single language, a single framework, and a cohesive set of APIs. React server components improve upon traditional rendering techniques while also overcoming their limitations. Now we have covered quite a bit, so let me simplify it with React server components and client rendering of the app. With wait for the entire page to finish rendering on the server. With RC architecture, server components take charge of data fetching and static rendering, while client components are tasked with rendering the interactive elements of the application. The bottom line is that the RC architecture enables React applications to leverage the best aspects of both server and client rendering, all while using a single language, a single framework, and a cohesive set of APIs. React server components improve upon traditional rendering techniques while also overcoming their limitations. Now we have covered quite a bit, so let me simplify it with the key takeaways. React server components introduce a new way of building React apps by separating components into two types, server components and client components. Server components run only on the server, accessing data and preparing content without being sent to the browser, which makes the app faster for users because less information needs to download. They can't manage clicks or interactivity directly. Client components, on the other hand, work in the user's browser and handle all the interactive parts of the app, like clicking and typing. They can also be rendered on the server for a fast initial load of the site. The setup helps make websites faster, more secure, and easier for everyone to use, no matter where they are or what device they're using. Now you might be wondering, this deep dive into the evolution of rendering in React is great, Vishwas, but how exactly does it help understand rendering in Next.js? What is the connection? Well, the connection is quite straightforward. The app router in Next.js is built around the RC architecture, meaning all the features and benefits we have discussed are already baked into the latest version of Next.js. By understanding the evolution of React's rendering, you now have the necessary background for the rest of the section, which will focus on Next.js. So, if you are feeling confident with the React rendering strategies we have learned so far, let's dive into rendering in Next.js in the next video. However, if you found any of the techniques difficult to understand, I recommend watching the videos a few more times. A little patience goes a long way, but I promise it will start to make sense. Alright, thank you for watching. If you're enjoying the content, please hit the like button and subscribe to the channel. I'll see you in the next video. In our previous video, we dived into React Server Components, which introduced a dual component model differentiating between server components and client components. In this video, we will put theory into practice by creating both types of components in a Next.js application. For this section on rendering, I have created a new Next.js project using the command npx create next app at latest, followed by the project name, which is rendering-demo. Once the command is executed, you should have a project similar to mine. Now, diving into the RC architecture and its integration with Next.js, it is important to note that, by default, every component in a Next.js app is considered a server component. This includes the root layout and the root page that come out of the box with a new Next.js project. Let's create a new component to verify this. Suppose we want to add a new about page to our application. We would create a new file called page.tsx within the about folder, within the app folder. Let's populate it with a basic React component. I will use the Pieces Explorer extension for the code snippet. We're going to insert a Next.js page component. Export default function page. Let's call this about page, and return an h1 tag that says about page. Just by doing this, you've created a server component. Let's add a log statement to verify this. Console.log about server component. If we head to the browser and navigate to localhost 3000/about, we don't see any log message in the browser console. Instead, we see the message in the terminal where we are running our application. It is clear a component is a server component. This component runs on the server, bringing along all the benefits of server components such as zero bundle size, access to server-side resources, enhanced security, better SEO, etc. But server components have their limitations. They can't interact directly with browser APIs or handle user interactivity. If we try to incorporate some state into our about page using useState, for example, name, set name, with a default value of an empty string, while making sure we import useState at the top, head back to the browser, you will see an error. This is because useState expects a client component environment, but our about page is a server component. If you think about it, server components cannot use state because they're rendered on the server where there is no concept of state as it exists in the browser. This again confirms the fact that every component created in Next.js is a server component unless specified otherwise. Let's leave the about page as a functioning server component and learn how to create a new client component. We'll make use of a new file, so within the app folder, dashboard/page.tsx, and export a simple component that uses state to manage a user's name. Once again, from Pieces Explorer, I'm going to insert a Next.js page component, change the name to dashboard page, import useState, create a state variable called name with an initial value of empty string. And for the JSX, we add an input element whose value is equal to the name state variable, and on change, we call set name passing in the input value. We then have a paragraph element that renders hello followed by the name. Now at the top of this file, we must include a directive, or to put it simply, a special instruction within the code. Within double quotes, use client. This directive acts as our ticket to cross the boundary from server to client side, and is what allows us to define client components. It signals to Next.js that this component, dashboard page, along with any components it imports, is intended for client-side execution. As a result, the component gains full access to browser APIs and the ability to handle interactivity. If we return to the browser and navigate to /dashboard, we see the component with its state working as expected. We do have the text, but the styling is not appropriate. Let's now shift our attention to a very important point about client components rendering behavior. Let's add a log statement within the dashboard component. Dashboard client component. In the home page, let's add a link to navigate to the dashboard page. So at the top, import link from next/link, and after the paragraph tag, I'm going to add the link component. The text is dashboard, and href is equal to /dashboard. Back in the browser, if we navigate to localhost 3000, we should see the dashboard link. Click on the link, and we see the log message in the browser's console. We have it twice because of React's strict mode. If we go back to the terminal, you can see there's no log message about the dashboard component rendering. However, if you were to reload the dashboard route, you can see we have the message in the browser's console again, but if we head back to the terminal, we see the same message here as well. As I mentioned in the previous video, client components are primarily executed in the client and have access to browser APIs, but they are also pre-rendered once on the server to allow the user to immediately see the page's HTML content rather than a blank screen. It is an optimization strategy that Next.js implements and is recommended by React. The name client component is indeed confusing, as a client component executes once on the server, but I'm confident it will not get in your way of learning React server components. A very important point to keep in mind. To summarize, in the React server component architecture, and by extension in the Next.js app router, components are server components by default. To use client components, you must include the useClient directive at the top. Server components are rendered only on the server, whereas client components are rendered once on the server and then on the client. Now that we understand how to define both server and client components in Next.js, in the next video, let's dive into the rendering lifecycle of server and client components in Next.js. If you're enjoying the content, please hit the like button, subscribe, and turn on notifications to stay updated. I'll see you in the next video. Welcome back, everyone. In our previous videos, we talked about server and client components in Next.js. In this video, we're going to learn about the
「けらが冷たい風にさらわれてゆく」「手を伸ばしても届かないけど」「君のエネ影が背中を押す」「この胸の奥深い場所で言えなかった言葉が叫んでる」「黒い星が瞬く空の下」「君の姿を探し続けた」「一人きりの帰り道の影が」「心をじわり蝕んでゆく」 少しずつ遠ざかるそっと抱きしめてそっと抱きしめて君がいない夜の静けさが僕を深く追い込んでくそっと抱きしめてそっと抱きしめてただそれだけが僕を救うのに星空の下一人きりで君を呼んでも届かない声そっと抱きしめて君のいない世界は寒すぎて誰これじゃ言葉を探しても気持ちだから回りしていく君の瞳に映る僕は壊れたパズルのようで重ねた時間が崩れてても残る思いはどうすればいい絡まったままの記憶たち答えを求めて迷ってる Heartbreak バラバラになったまま止まれない Heartbreak 君に届かないこの叫びがこぼれ落ちたピース拾い集め形を戻そうと手を伸ばしても見えない縁が心を裂くひび割れた気持ちに触れられない君が笑うその瞬間さえ僕には遠すぎるリアルでもう一度戻せるなら何をするこの胸の答えが今も問う冷たい風が胸を刺して隙間に忍び込む夜の影伝えたかったあの日の言葉今更遅すぎるけど君に触れたその記憶だけ僕を支えていたはずなのに好きじゃ足りない感情たち行き場を失って泣いている Heartbreak バラバラになったまま止まれない Heartbreak 君に届かないこの叫びが Heartbreak 夜に溶けてバラバラなままでも探してる Heartbreak 君のそばで形を取り戻す日を願って Heartbreak 夜に溶けてバラバラなままでも探してる Heartbreak 君のそばで揺れるカーテン朝焼けの光眠りの中で君を探してる伸ばした手には空気しかないよこの世界には君はいないの夢の中の恋は叶いこの愛君に触れたくても届かない迷いが心をかき乱してく出口のない思いどうすればいい現実の闇が心を包むだけど夢の中君だけが映る目を覚ますなね誰も言わないでこの幻想の中生きていたいだけ時計の針が進む音 来るたびにこの世界は壊れ止まらないループ覚めたくない夢願うよ永遠に君といたいだけ静かな部屋で聞こえる君の声幻だって分かっているのに昨日の笑顔胸の中にある瞳を閉じてまた君に会う夢の中の恋叶いこの愛君に触れたくても届かない迷いが心をかき乱してく出口のない思いどうすればいい一つの瞬間時が止まるだけ君と私が重なる空間覚めたら全てが消えてしまうならそれでもいいよ夢で生きるから夢の中の恋は叶いこの愛君に触れたくても届かない迷いが心をかき乱してく出口のない思いどうすればいい夢に落ちるたび君に会えるからこのままずっと覚めないでほしい最初は不安だった何も見えなくて君の心に触れるたび怖さが増した言葉で伝えてほしいそれが愛だと思ってただけど君は違う仕草が全てを教える優しさで包まれるたび胸が満たされていく何も言わなくても君が愛をくれる言葉なんていらない君の瞳が語るその手のぬくもりが全てを伝える愛の言葉以上の何かで僕を包む君の愛が心に響いてゆく言葉よりも深く届く君の優しさ小さな仕草が僕を動かすハグ一つで感じるその想い音もない愛が心を満たす二人の時間が答えになる見えないけどそこにある光言葉で飾らない君が好きだよそのシンプルな優しさが愛の証明胸の奥に灯る光消えないぬくもり言葉じゃ追いつけないほどの愛を知った二人だけの世界がそこにある沈黙さえ心地よく感じる夜言葉なんていらない君の瞳が語るその手のぬくもりが全て 君の声が遠く聞こえる夜、画面越しの笑顔がどこか寂しい。手を伸ばしても触れられない距離が僕たちの心も離していく。君と見たあの未来はまだ同じ形で輝いてる。遠い空に問いかけても答えは風に消えていく。もう一度もう一度だけ君と笑い合える未来を信じたい。もう一度もう一度だけ手をつなぎたいと願う夜に、離れた距離が心を冷やす。君の言葉に潜む沈黙が怖い。全てがうまくいくと信じてたのに、いつの間にかずれた時計の針。僕の気持ちが届いているの？君の想いはどこにあるの？この距離を超えられる答えがもう一度見つかるなら。電話越しの声がかすれていく。僕の名前を呼んでほしいのに、君のチンババに耐えきれなくて、記憶の中の君を探してる。離れても続くと信じた日々、それでも今心が揺れてる。触れられない君の笑顔をまだ忘れたくない。もう一度もう一度だけ君と笑い合える未来を信じたい。もう一度もう一度だけ手をつなぎたいと願う夜に、もう一度声を聞かせて、もう一度あの日に戻れるなら、遠い距離を越えたその先で君と一緒にいられると信じたい。夜の鏡に映る僕、君の影だけ探してしまう。秘密の扉の向こう側、君の骨が眠っているの。消えた言葉が胸を刺して、冷たい風が頬をなぞる。触れられない距離の君はどこで僕を見ているの？君の本音を知りたいの。 君の答えをただ待っている君の本音を知りたいの君の本音を知りたいの言葉の裏に隠れてる君の本音を知りたいの君の本音を知りたいの僕を迷わせる君のかけら君の本音を知りたいの夜の静けさが胸を満たしてて僕はただ叫び続けるだけ君の本音を知りたいのもしも過去に戻れるなら、君とすれ違うその時を変えたい初めて出会った瞳の中に感じたものなんて今はもう消えたあの時の笑顔も優しさも思い返せばただの思い少しなかったことに全部消して君と出会うその前に戻りたいあの日の想いもこの痛みも全て無意味だったとわかるから今は君が嫌いだ大嫌い大嫌いあの過去の中に戻れたとして変えられるのは記憶のかけら君と交わした言葉も温度も全部ゼロに戻してしまいたい後悔だけが胸に積もる夜愛があった日々も今では嘘嫌いになることで核になれるならその選択肢を選びたいだけ好きだった気持ちが痛みに変わり君にの名前が呼べない夜が続くもしもあの日がなかったなら今はもっと自由でいられたはず笑い合った瞬間さえ記憶の底に封じて消してしまいたいなかったことに全部消して君と過ごした時間も消えていい愛しさも憎しみも忘れたくて今は君を遠ざけて生きたいだけ過去に戻れるならそれがいいなかったことに全て消えて君の声も記憶も風に流れる今は君が嫌いだそれでいいさよならすらいらないもういらない夜のカフェで交わす言葉君の笑顔遠い気がして一歩出せば壊れる距離それが僕らのルールなんだ触れた指視線そらして同じ場 場所で違う想い伝えたくてでも言えなくて曖昧なまま夜が包むそんなものだよそんなものだよ君と僕のこの針の距離近くても遠くても届かないそんなものだよそれが全て夜に響く君の声些細な会話に隠れる思い友達の線に誰のもの超えたいけれど壊れる気がして曖昧な笑顔の裏に弾む知りたいけど言えないジレンマ君の中の本当の気持ち探しながらたださまようだけ帰り道影が揺れてる何も言えず肩を並べてこの瞬間続けばいいなんて思う僕の弱さに気づく君の笑顔真実知れば傷つくこと分かってるのに気づかないふりを続けてる夜が静かに全てを隠すそんなものだよそんなものだよ君と僕のこの愛がの距離近くても遠くても届かないそんなものだよそれが全てそんなものだよ君との距離この夜明けても何も変わらない友達一生恋人未満そんなものだよそれが現実僕の涙が言ってる君の気配を探している触れられないぬくもりだけが胸の奥で小さく震える崩れた時の止まる音君の声が消えた幻見えない未来に触れるたびこの世界が少し光るそれでも美しい世界君がいないこの夜でも壊れてく僕の記憶がそれでも美しい世界を描くこぼれたかけら一つ集めて君の残像そっと並べた見えない道を一人歩いて君の笑顔が消えないまま夜の静けさ溶ける言葉消せないものは胸の痛みでもこの闇が続く先には新しい光があると信じたい冷たい風が胸を吹き抜け君の名前が響いてくる言えなかった言葉のかけら空の彼方で僕を呼んでる孤独の中で見つけた光君が残した愛の形悲しみの海に沈む夜でも僕はきっと歌い続けるそれでも美しい世界君がいないこの夜でも壊れてく僕の記憶がそれでも美しい世界を描く君がいた頃の世界は今も胸の奥で色を変えてそれでも美しい世 静かすぎる夜がアンニュイ僕の心はどこを見てるただのノイズか誰かの声君の名を待っている光る画面映るネーム何度も期待しては消えてゆく突然のコールに揺れる君からならいいのに突然のコール突然のコール君の名前が頭に浮かぶ突然のコール突然のコールでも君からコールは来ない待ち続けるだけの毎日君じゃなど満たせない鳴らないベルが心を試す君の声だけが色を変える突然に来たらどうするんだろう言葉を探す前に胸が騒ぐこんなにも単純なことで世界が変わるなんて信じられない風が冷たく頬なでる過ぎ去った日々の記憶が響く突然に鳴ったベルの音はいつも僕を惑わせる君の声が遠く感じても触れられない距離を越えたい突然の期待に揺れる心その瞬間が欲しいだけ突然のコール突然のコール君の名前突然のコール突然のコールでも君からコールは来ない突然のコール君からなら僕の夜が光に変わる突然のコール願うだけでまたシェイシャープに戻っていくすれ違っただけ胸が鳴るこんな気持ち初めてなんだ目が合うたびキラキラする嘘みたいな特別な感覚何度も自分に問いかけてみるこれが運命じゃないなら何答えなんてなくてもいいんだただこの時に生きていたい運命だからときめくんだよこんな時々止まらない運命だから離れたくない君しかいない嘘みたい運命をしか入れないからこの気持ち今も輝いてる息をするだけで感じる君胸の中で響く音のリズム偶然なんかじゃない託しに変わるこれが答えだと叫びたくなる君と過ごす時間の輝き忘れられない夜の記憶何度も思い出してドキドキするこんな感じが気なのかもね今までの自分じゃ考えられないこんなにも何かに夢中になる他の誰でもない君だけが僕の世界を変えてゆくんだどんな未来が待っているのかそれさえ怖くなくなるんだ君といれば全てがきらめくこんな奇跡はもう二度とない運命だからときめくんだよこんなドキドキ止まらない運命だから離れたくない君しかいない嘘みたい運命よしかありえないからこの気持ち今も輝いてる夜空に光る星のように君といるだけで満たされる運命を感じる心の中でこのときめき永遠に続いて運命だからときめくんだよこんなドキドキ止まらない運命だから離れたくない君しかいない嘘みたい運命よしかありえないからこの気持ち今も輝いてる る瞬間が全てなんだ。運命に導かれて生きてる。僕の涙が静かに言う。君の気持ちはどこにあるの。触れることのないぬくもりだけが胸の奥で冷たく震える。壊れた時の止まった音、君の声は幻に消えた。見えない未来を探すたびに気持ちの影だ僕を裂いてく。それでもこの気持ちがある。君がいないこの世の中で崩れてゆく僕の世界ごと。それでもね気持ちが叫ぶ。散らばる気持ちどうすればいい。君が残したものは皇居だけ。触れるたび深まる冷たさが僕をさらって闇へ落としてく。気持ちは嘘つき知りたくないのに胸の中で叫ぶ消えない声。未来なんて信じられないけどこの闇の中で探し続ける。冷たい風が胸を抜ける。君の気持ちは遠くで笑う。言えなかった言葉のかけらが空のどこかで僕を呼んでる。孤独の中で探した光、君が残した残酷な愛。悲しみの海に沈む心、気持ちだけが僕を壊してく。それでもこの気持ちがある。君がいないこの夜の中で崩れてゆく僕の世界ごと。それでもね気持ちが叫ぶ。君がいた頃の世界の色が今は胸の奥で滲んでいる。それでも気持ちだけは残る。僕の中で声を響かせる。ねえアスファルトが消えるくらい君の記憶がピンクに変わって解けないのパズルのピースみたい。また僕の手の中で消えてく。ぬくもりも雨に消えて君はどこの空へ飛んだの。守れなかった秘密、星だって知らない秘密。守れなかった秘密、キラキラ胸でまた秘めてる。守れなかった秘密の言葉、君の涙が空を飾る。傷つけたのはこの指先、気づいた時には夢の中。約束なんて空っぽの箱で未来の絵本を履けなかった。戻らない道で迷子になって記憶の君はウインクしてる。守ると言ったその言葉が 今の私をふわり縛るだけ静かな風が白爪草揺らす君が隣にいた空の色守れたはずの雲の橋渡って二人の場所に帰りたい忘れようとしても消えない君の声は透明な水玉守れなかった秘密の手紙心に滲んでく守れなかった秘密の言葉キラキラ胸で巻いてまだ響いてる守れなかった秘密の言葉君の涙が空を飾る守れなかった秘密の意味をまだ探してる僕がここにいる守れなかった秘密の方法さ君の影だけが夜を踊らせる めて気づいた君が好きだとでもその人も君を見てたね一つの光に二つの影が静かに重なる冷たいよ伝えたい言葉胸で消えるたび声にならない想いだけが 然知ってしまった秘密それは痛みの形してただ静かに胸の奥で言葉にならず響いてたずっと黙っていたかったこの想いにふわれないでそっと離れる理由はきっと君もわかるはず遠い記憶が重なるたびに心に増えるひび割れたガラス知らなければよかった秘密が静かに夜を染めてゆく呼びかける声は聞こえないまま隠した涙の跡が残るでも言葉にすれば崩れるからただ遠ざかる影を見てた冷たい月が照らす道で振り返る雪さえなくて歩 君と歩いてふと気づけば暗くなる空時間の流れにただ身を任せ懐かしい風が頬を撫でる今日は特別じゃないけれど君と過ごすだけで何もかもが輝いて見えるただそれだけで心が満たされるいつものようにただ君と過ぎてゆく日々に溶けてゆく何も恐れずただ信じてこの手を離さないでいてほしい街の明かりが揺れる中で二人の足音だけが響く何気ない日々に隠れた宝物君とならどんな世界でもどうしようもないこの感じが忘れられない変わらないいつものようにただ君と過ぎてゆく日々に溶けてゆく何も恐れずただ信じてこの手を離さないでいてほしい一緒にいるだけで不安なんて消えてゆく手を伸ばす先に君がいるそれだけでいいそう思うんだいつものようにただ君と過ぎてゆく日々に溶けてゆく何も恐れずただ信じてこの手を離さないでいてほしいいつもの夜に君とだけ過ぎてゆくすべてが美しい隣に君がいるだけで何気ない景色が変わる深夜のカフェで交わす言葉それだけで満たされる心特別じゃなくていいただこの瞬間が大事未来のことは知らなくても今を感じていたいだけただそれだけでいい君の笑顔とこの好き何もいらないここにある二人だけの
rendering lifecycle of server and client components. In simpler terms, we will explore how they come to life on your screen. Understanding this process is not mandatory for building Next.js apps, but it is like knowing what happens in the kitchen before your food arrives at the table. Not necessary for enjoying your meal, but definitely interesting. For React server components, it is important to consider three elements: your browser, which is the client, and on the server side, Next.js, which is the framework, and React, which is the library. Let's break down the initial loading sequence step by step. When your browser requests a page, the Next.js app router matches the requested URL to a server component. Next.js then instructs React to render that server component. React renders the server component and any child components that are also server components, converting them into a special JSON format known as the RSC payload. If you inspect the network tab when navigating to a route, you will come across this special JSON format, which is the RSC payload. During this rendering, if any server component suspends, React pauses rendering of that subtree and sends a placeholder value instead. Meanwhile, client components are prepared with instructions for later in the lifecycle. Next.js uses the RSC payload, which includes the client component instructions, to generate HTML on the server. This HTML is streamed to your browser to immediately show a fast, non-interactive preview of the route. Alongside, Next.js streams the RSC payload as React renders each unit of UI. In the browser, Next.js processes the streamed React response. React uses the RSC payload and client component instructions to progressively render the UI. Once all the components and the server components output has been loaded, the final UI state is presented to the user. Client components undergo hydration, transforming our app from a static display into an interactive experience. This is the initial loading sequence. Next, let's take a look at the update sequence for refreshing parts of the app. The browser requests a refetch of a specific UI, such as a full route. Next.js processes the request and matches it to the requested server component. Next.js instructs React to render the component tree. React renders the components similar to the initial loading. But unlike the initial sequence, there is no HTML generation for updates. Next.js progressively streams the response data back to the client. On receiving the streamed response, Next.js triggers a re-render of the route using the new output. React reconciles or merges the new rendered output with the existing components on screen. Since the UI description is a special JSON format and not HTML, React can update the DOM while preserving crucial UI updates such as focus or input values. This is the essence of the RSC rendering lifecycle with the app router in Next.js. If we dive deeper into rendering, we have three server rendering strategies: static rendering, dynamic rendering, and streaming. Let's take a closer look at each of these next. Thank you for watching. Please consider subscribing to the channel, and I'll see you in the next one. In the previous video, I briefly mentioned the three server rendering strategies in Next.js. In this video, we will dive into the first one, which is the first one, which is static rendering. Static rendering is a server rendering strategy where we generate HTML pages at the time of building our
Hey bro, Metcon.
application. This means all the data and content for a web page are prepared in advance. This approach allows the page to be built once, cached by a CDN, and served to the client almost instantly. This optimization also enables use, resulting in a significant performance boost for your application. Static rendering is particularly useful for blog pages, e-commerce product pages, documentation, and marketing pages. Now that we understand what static rendering is and when to use it, the next question is, how do we use it? Or how do we inform Next.js that we want to statically render a particular route in our...
Right now I'm not coding anything. I'm just preparing for my interviews and learning Next.js concepts and writing down the questions. But after this, I'll work on a project, personal project that I'm working on for the past week.
application. Here's the good news. Static rendering is the default rendering strategy in the app router. This means all routes are automatically prepared at build time without additional setup. You might be wondering at this point, Vishwas, Throughout this video, you have mentioned that HTML is generated at build time. But there is no build for our application yet, is there? Aren't we running our application in development mode? This is a fantastic question to have, so let's spend a minute to understand the distinction between a production server and a development server. For production, an optimized build is created once and you deploy that build. Code changes are not made on the fly once it is deployed. A development server, on the other hand, focuses on the developer experience. We should be able to make changes in our code and see those changes immediately reflected in the browser. We can't afford to build our application once, make changes, rebuild, and so on. Therefore, the Next.js team decided that for production builds, a page will be pre-rendered or statically rendered once when we run the build command. However, in development mode, a page will be pre-rendered or statically rendered for every request. So if you visit the home page, it is pre-rendered and served. Refresh, and the page is pre-rendered and served again. This ensures that code changes are reflected in every request. It might seem strange when I say this, but you don't have to worry about static rendering in development mode. It is more important to understand how it works when you build your application. Before we dive into the build process though, let's clean up by deleting the .next folder generated during development. In the about page, let's also render the current time as it helps prove a point. New date.toLocale time string. Now, in the terminal, run the command npm run build. This command creates an optimized production build of our application. The output folder, once again, is the .next folder, but this time, the content will be different from those of the dev script. There are quite a few things to cover about the build process, so let's start with the terminal output. It displays information about each route in our application with 3 columns: route, size, and firstload.js. Route refers to the route itself, so about our dashboard, for example. Size refers to the size of the assets downloaded when navigating to the corresponding route client side in the browser. And firstload.js refers to the size of assets downloaded when loading the page from the server. The firstload.js shared by all includes the CSS from globals.css, some runtime code, framework code, to modules vendor code like React, for example, and some code related to the routes and components in our application. This is shown as a separate metric, with the overall size being 84.2 kilobytes. For the individual routes generated, we see the root page corresponding to page.tsx in the app folder with a size of 11.2 kilobytes. But if you navigate to the home page in the browser, both the 11.2 KB and the first load shared bundle of 84.2 kilobytes are downloaded, resulting in a first load.js size of 94.4 KB. We also have a 404 not found page, not created by us, but generated by Next.js to render when the route is not defined in the app router. The size is 885 bytes, and the first load is 85.1 KB. The about route, which contains a server component, is 136 bytes when you navigate client side, and 84.3 KB when you load the page from the server. The dashboard route, which contains a client component, is slightly bulkier with 370 bytes and 84.5 KB from the server. Hopefully, the table is now clear. For the next part, let's focus on the legend. Next.js provides a legend for the type of routes generated. For our root route, which is page.tsx in the app folder, we have a hollow circle. This indicates static rendering, where the route is automatically pre-rendered at build time as static HTML content. This is also the case for our 404 not found page, about route, and dashboard route. This indication helps you understand which routes are pre-rendered at build time, especially when starting out with Next.js. Let's now move on to the last part, which is understanding the build output. Next.js generates the build output into the .next folder, which contains various files and folders essential for serving our application to incoming requests from the browser. Here, we can primarily focus on the server and static folders. Within the server folder, we have an app folder corresponding to the app router. Here, let's focus on the important file types. First, the HTML files. Our build info shows that the root page is a static HTML page. The same can be found in the app folder as index.html. Similarly, we have 404 not found in the terminal, indicated as static rendering, and we can find the not found.html file in the app folder. We have about.html, corresponding to the about route containing an h1 element, and dashboard.html corresponding to the dashboard route containing a heading, an input, and a paragraph. Remember, even client components are pre-rendered as an optimization step, and that is the reason we see the client component HTML. Besides HTML files, it's also important to know the RSA payload for each route. For example, we have about.rsc for the about server component, and dashboard.rsc for the dashboard client component. This special JSON format generated by React for each route is a compact string representation of the virtual DOM. It includes abbreviations, internal references, and encoded special meanings. For a server component, the payload
You mean you wrote a blog or something?
includes the render result of the server component, like the h1 tag with the text about page, the JSX from our component. For
Yeah, Next.js 15 just recently dropped, I think a month ago, right? So if you wrote a blog about this, I would love to read it. Can you like send it through chat, or where can I find it? Any links? Because I recently started watching, not watching, I recently started working with Next.js. Like it's been like maximum 2 months started using Next.js, so I'm fairly new to this, but like worked on 2 projects like half brokenly, because I like to like jump on projects more than watching videos. So while I was working, I realized that Next.js actually works pretty differently to React. So, and also I had interviews, so I thought like uh, like read about these concepts in a video, like, and write the questions. It's from 2022. No worries, man. You can still drop it. I would love to read it.
For a client component, however, the payload includes placeholders or instructions where client components should be rendered, along with references to their JavaScript files. For instance, the dashboard route, which is a client component, contains
Yeah, maybe. I think links are not accepted in like comments. So, like, where did you write the blogs? If you have any username or something I can find, just drop it. I will find it.
a reference to the code for the dashboard component. If we were to search dashboard page in the RSC payload, we don't find it. However, if we track this page -3c05 file in static chunks app dashboard, so static chunks app dashboard page 3c05, you can see we have the h1 tag with the text dashboard page. This is the file
Wait, I'll search. Matteo Ziffer. This one. Yeah, I think this one. This one. Got it. I'll surely read this because like I was speed running this playlist, and after like 50 or 50 videos, this one I don't understand at all. So I'll read it. By the way, if it's okay, can you like join our Discord? Like you seem very knowledgeable guy in Next.js, so where's the edit? Create. I'll put the link in the description. Okay. Refresh the like the live stream. You can see the link in the description. Yeah, sure, man. Thank you for dropping by the way. I'll follow you on GitHub and LinkedIn. What happened to my internet?
referenced in the RSC payload.
Wait.
And this file contains the component code necessary for reconciliation and hydration. Alright, if the build output is clear, let's serve our application from this .next folder. In the terminal, run the command npm run start. This runs our application on localhost port 3000. In the browser, with the network tab open in the DevTools, click on empty cache and hard reload. You can see the preview of the HTML page, and in the response, you can see the HTML code. Apart from this HTML, I want to draw your attention to the RSC file, the one for dashboard. This is essential for building the UI on the client side when we navigate to /dashboard using the link. The component code for the dashboard, represented by page 3C05, has also been downloaded. If we navigate to the dashboard route, you will notice that the route is rendered without the need to download any additional resources from the server. The initial load includes everything required for client-side navigation. However, we must ask the question, how does Next.js know to download the dashboard component code ahead of time? Well, this is due to a feature known as prefetching in Next.js. Prefetching is a technique used to preload a route in the background before the user navigates to it. Routes are automatically prefetched as they become visible in the user's viewport, either when the page first loads or as it comes into view through scrolling. For static routes, the entire route is prefetched and cached by default. Therefore, when we load the homepage, Next.js prefetches the about and dashboard routes, about if you did include a link, keeping them ready for instant navigation. But what about dashboard.html in the server folder? We did not download that. Well, this file is served when you directly navigate to the page in the browser. For instance, if you directly load the URL, localhost 3000/dashboard, you receive the HTML for the dashboard, along with the code shipped to the client for hydration. Finally, I want you to observe the time rendered in the About page. It is 7:36 p.m. This is going to remain the same regardless of how many times you refresh the page, as it was rendered when the application was built. You can see the same in the HTML file. We will explore more about static rendering when we deal with data fetching in the next section, but to summarize what we have learned in this video, static rendering is a strategy where the HTML is generated at build time. Along with HTML, the RSC payload is created for each component, and JavaScript chunks are produced for client-side hydration in the browser. If you navigate directly to a page route, the corresponding HTML file is served. However, if you navigate to the route from a different one, the route is created client-side using the RSC payload and JavaScript chunks without any additional request to the server. Static rendering is great for performance, and use cases include blogs, documentation, marketing pages, etc. I understand that this concept might be challenging to grasp fully. If you're feeling slightly confused, I highly recommend rewatching the previous few videos, running the same code on your local machine, and I guarantee you'll gain a much better understanding of static rendering in Next.js. My goal is to explain not just the what, but also the why. Why we write the code we. For our second server component pattern, let's explore the integration of third-party packages. Since server components introduce a new paradigm in React, third-party packages In the previous video, I briefly mentioned rendering is a strategy where the HTML is generated at build time. Along with HTML, the RSC payload is created for each component, and JavaScript chunks are produced for client-side hydration in the browser. If you navigate directly to a page route, the corresponding HTML file is served. However, if you navigate to the route from a different one, the route is created client-side using the RSC payload and JavaScript chunks without any additional request to the server. Static rendering is great for performance, and use cases include blogs, documentation, marketing pages, etc. I understand that this concept might be challenging to grasp fully. If you're feeling slightly confused, I highly recommend rewatching the previous few videos, running the same code on your local machine, and I guarantee you'll gain a much better understanding of static rendering in Next.js. My goal is to explain not just the what, but also the why. Why we write the code we do, and why things happen the way they do. Thank you for watching, and if you're finding the videos helpful, please do leave a like and subscribe to the channel. I'll see you in the next one. In the previous video, we learned about the first server rendering strategy, namely static rendering. In this video, let's dive into the second strategy, which is dynamic rendering. Dynamic rendering is a server rendering strategy where routes are rendered for each user at request time. It is useful when a route has data that is personalized to the user or contains information that can only be known at request time, such as cookies or the URL's search parameter. In the previous video, we learned about the first server rendering strategy, namely static rendering. In this video, let's dive into the second strategy, which is dynamic rendering. Dynamic rendering is a server rendering strategy where routes are rendered for each user at request time. It is useful when a route has data that is personalized to the user or contains information that can only be known at request time, such as cookies or the URL's search parameters. News websites, personalized e-commerce pages, and social media feeds are some examples where dynamic rendering is beneficial. Now that we understand what dynamic rendering is and when to use it, the next question is how do we use it, or how do we inform Next.js that we want to dynamically render a particular route in our application? It turns out, during rendering, if a dynamic function is discovered, Next.js will automatically switch to dynamically rendering the whole route. In Next.js, the dynamic functions are cookies, headers, and search params, which acts more like a prop available for every page. Using any of these will opt the whole route into dynamic rendering at request time. Let's go back to VS Code and write some code to understand better. In our about component, let's import and include the cookies dynamic function. So at the top, import cookies from next/headers, and within the component, const cookie store is equal to invoking the cookies function. Const theme is equal to cookie store.get, and let's assume there is a cookie called theme. Let's log theme to the console. Now what we do with the cookies function is not really important right now. We are including it to ensure Next.js dynamically renders this about page. With this code in place, let's build our application and inspect the output from dynamic rendering. Let me delete the .next folder, and in the terminal, run the command npm run build. This takes a couple of seconds to generate the .next build folder. Now for the first part, let's make sense of the build output in the terminal. Similar to the previous video, we have a list of all the individual routes generated. Our focus though is on this about route. It has a lambda symbol beside it. And if you take a look at the legend below, lambda stands for dynamic rendering, where we server render on demand using Node.js. The next point to keep in mind is that dynamically rendered pages are not statically rendered at build time. So if we inspect server app, we see the dashboard.html page as before, but we don't see the about.html page. This behavior is as expected. For the final part, let's start the application. In the terminal, run the command npm run start. If we now refresh/about, the page is pre-rendered, and you can see the log statement in the terminal, the cookie name and value, as well as the about server component log statement. In the network tab, we can see the preview, as well as the response, which contains the HTML. Refreshing this page will render the latest time. But the HTML file is not generated in the server. Since a new page is built for every request, there's no need to generate a page into the build folder. You can see we still don't have about.html. What we have just seen might seem trivial after understanding builds for static rendering. However, like I mentioned earlier, building our application and running the build application is as close as we can get to a production deployment, so I wanted to make sure you understand how it works. Now, similar to static rendering, we will explore more about dynamic rendering when we deal with data fetching in the next section. But to summarize what we have learned in this video, dynamic rendering is a strategy where the HTML is generated at request time. Next.js automatically switches to dynamic rendering when it comes across a dynamic function in the component, such as cookies, headers, or the search params object. This form of rendering is great for when we need to render HTML personalized to a user, such as a social media feed. What is great with Next.js is that as a developer, you do not need to choose between static and dynamic rendering. Next.js will automatically choose the best rendering strategy for each route based on the features and APIs used. Alright, thank you for watching. Please consider subscribing to the channel, and I'll see you in the next one. In this video, let's explore the third and final server rendering strategy, which is streaming. Streaming is a strategy that allows for progressive UI rendering from the server. Work is divided into chunks and streamed to the client as soon as it's ready. This enables users to see parts of the page immediately before the entire content has finished rendering. Streaming significantly improves both the initial page loading performance and the rendering of UI elements that rely on slower data fetches, which would otherwise block the rendering of the entire route. This concept may seem familiar as we covered it in an earlier video titled Suspense for SSR when discussing React's rendering techniques. The difference now is that we are focusing on Next.js, where streaming is integrated into the Next.js app router by default. Let's dive into the code and learn how to manually create suspense boundaries in our application and rely on streaming for better performance. To save time, I have prepared the code beforehand. I've created a new route called product detail, which renders 3 elements: an h1 tag that reads product detail page, a product component, and a reviews component. I've defined these 2 components in a folder named components within the source folder. Here is a spoiler alert. With the app router, we can use async await with React components. We will dive into this in a different section, but for now, understand that I am intentionally delaying the rendering of the product component by 2 seconds and the reviews component by 4 seconds. Imagine this simulates the time taken to fetch data and render the component. With this setup, let's start the dev server. In the browser, navigating to /product detail shows that the page takes a while to render the h1 tag along with the 2 components JSX, product and reviews. If I refresh again in the network tab, you will notice that the time waiting for server response is slightly over 4 seconds, indicating that the data for the entire page is fetched before sending the response. Now let's enhance this with the streaming strategy supported in the app router. All we need to do is import the suspense component and wrap the slow components with suspense, and Next.js handles the rest. So in product detail page.tsx, import suspense from React and wrap both product and reviews component. Let's also add fallback text, which is a paragraph element loading product details, and similarly loading reviews. If we return to the browser and reload the page, we immediately see the page heading followed by the product detail component and then the reviews component. The time waiting for server response has significantly decreased to just 91.25 milliseconds. Let me reload the page so you can closely observe the UI. Refresh, page heading, 2 seconds in for the product component and 4 seconds in for the reviews component. This showcases the ability to progressively render HTML from the server to the client. This is what streaming is all about. Alright, this concludes our discussion on server rendering strategies in Next.js. We have one more very important topic to cover in this section on rendering, so let's tackle that in the next few videos. Thank you for watching, and I'll see you in the next one. Welcome back. Now that we have a solid understanding of React server components and the dual component model, let's focus on server and client composition patterns. I will provide a brief overview in this video, and we will dive deeper into some of the use cases for server and client components in the upcoming videos. We will start with server components, which are perfect for tasks like fetching data, directly accessing backend resources, protecting sensitive information on the server, and keeping large dependencies server-side, which helps in reducing client-side JavaScript. On the other hand, client components are best used for adding interactivity, handling event listeners, managing state and lifecycle effects, using browser-exclusive APIs, using custom hooks, and using React class components. While these use cases might seem straightforward, there is more to explore to understand how to effectively use them. Let's dive into the details starting next video. For our first server component pattern, let's talk about the separation of server-only code. When building Next.js applications, certain code is intended to execute only on the server. For instance, you might have modules or functions that use multiple libraries, use environment variables, interact directly with the database, or process confidential information. Since JavaScript modules can be shared between both server and client components, it's possible for code that's meant only for the server to unintentionally end up in the client. If server-side code gets bundled into the client-side JavaScript, it could lead to a bloated bundle size, expose secret keys, database queries, and sensitive business logic. It is crucial to separate server-only code from client-side code to protect the application's security and integrity. To prevent unintended client-side usage of server code, we can use a package called server-only to provide a build time error if developers accidentally import one of these modules into a client component. Let's dive into VS Code and understand with an example. Let's begin by creating a server and client component. In the app folder, create server route/page.tsx. Define a simple React component using Pieces extension. Pieces Explorer, TypeScript. Insert a Next.js page component. Next, in the same app folder, create another file, client route/page.tsx, and insert another React component using Pieces. For the server component, let's call this server route page, and for the client component, client route page, and at the top, add the use client directive. Since we will be creating plenty of client components in the future, let's convert this into a Pieces snippet for future use. Pieces, save to Pieces. Next, in the source folder, create a new folder named utils with a file, serverutils.ts. Here, let's define a function intended solely for server-side use. Our focus here is on the concept of server-only code, not the function's implementation details. Therefore, we will create a function with a simple log statement and return a string value. This function might depend on various NPM packages or custom utilities designed for server-side logic, use environment variables for API keys that shouldn't be exposed to the client side, make calls to a database to retrieve data, or process business logic, algorithms, or calculations that should remain on the server side. We return the result. Now, let's import and invoke this function in a server component, which is our page.tsx file in the server route folder. So within the component, const result is equal to server-side function with parentheses, and make sure to import server-side function from utils/serverutils. For the JSX, let's bind result to a paragraph tag. Let's also add a log statement, server route rendered. Back in the browser, if you navigate to localhost 3000/server route, we don't see the log message in the browser, but we do see it in the terminal because the page component is a server component. I hope this is clear. Next, let's include the function in our client-only route, and this is a client component. So const result is equal to, we call server-side function, bind result to a paragraph, and of course import the function at the top. I'll also add a log message, client route rendered, similar to the message we had for server route. Back in the browser, if you navigate to /client route, we see the log messages in the console. We do see them twice because of React's strict mode, which we can safely ignore as the built application would output only once. In the terminal, we also see the same log statements, as every client component is also rendered once on the server to generate the initial HTML. However, given the nature of the operations in server-side function, it's crucial to ensure that this code executes only on the server. If this code were included in the client-side bundle, it could lead to performance concerns due to a larger bundle size and heavy computations, which could degrade the user experience. Additionally, it could pose security risks due to sensitive logic and data exposure, and could lead to functional errors, as some server-specific logic might not work as intended in a browser environment. To ensure that this function remains server-side only, we can use the server-only package. In the terminal, run npm install server-only. When we import server-only in a module, it ensures that the module causes a build time error if it is included in the client-side bundle. So at the top, import server-only. Now, if a developer accidentally imports this module into a client-side component, like our client route here, you can see the build process will fail, alerting them to the mistake and preventing potential issues related to exposing server-only code to the client. You can see the error in the browser as well. In summary, maintaining a clear boundary between server-only and client-side code is crucial, especially when dealing with sensitive operations or data. Using the server-only package enforces this separation and helps maintain your application's security, performance, and reliability. Thank you for watching, and I'll see you in the next one. For our second server component pattern, let's explore the integration of third-party packages. Since server components introduce a new paradigm in React, third-party packages in the ecosystem are gradually adapting, beginning to add the use client directive to components that rely on client-only features, marking a clear distinction in the execution environment. However, it is important to note that many components from NPM packages, which traditionally leverage client-side features, haven't yet integrated this directive. The absence of use client means that while these components function correctly in client components, they may encounter issues or might not work at all within server components. To address this, you can wrap third-party components that rely on client-only features in your own client components. Let's dive into VS Code and understand with an example. For this example, we will use the React Slick NPM package, which exports a React carousel component. The carousel component uses client-side features. First, install the packages, React Slick, Slick Carousel, and the types. So npm install React Slick, Slick Carousel, at types/React Slick. Next, scroll down and open the playground example. We're going to copy and paste the sample code. Copy the code from image_slider.jsx to client route page.tsx, which is a client component. Start with the imports, followed by the JSX. We can remove the CSS import line and instead copy the CSS from image_slider.css to globals.css. Finally, if you're having problems with placeKitten, we can replace this with pixem.photos. In the browser, if you visit localhost 3000/client route, you should see a first image. in global CSS, change the color from black to white, and you should see the 2 chevrons. Now all the images remain the same, but the carousel is working as expected. Back in VS Code, let's now try to integrate the carousel directly into a server component. So paste this same code into the server route page.tsx file. First the imports, and then the component code. I'm going to comment out server-side function from the previous video. If you go back to the browser and navigate to localhost 3000/server route, you'll notice an issue. This is because the slider component is using client-side features, but the library code doesn't have the useClient directive. One solution is to add the useClient directive within the server route, but then you cannot use server-only features like database calls, secret environment variables, etc. To resolve this, you must encapsulate third-party components that depend on client-only features within your own client components. Let me revert the code in server route, and instead, in the components folder, create a new file, image_slider.tsx, copy and paste the same code as before, including the useClient directive at the top. In our server component, we can now simply invoke the image slider component. So we still have a server component, but now with one nested element behaving as a client component. If we head to the browser, we can see /server route. We have the carousel working as expected. Next and previous. We will see the same message from Pixum, but if you have local images to work with, you can see the different images as part of the carousel. In summary, third-party packages in the React ecosystem are in a transitional phase where numerous components from NPM packages haven't yet adopted the useClient directive. Wrapping such components in our own client components will allow us to leverage the ecosystem of third-party packages while adhering to the new server components model. Alright, thank you for watching. If you're enjoying the content, please leave a like and subscribe to the channel. I'll see you in the next video. For our last server component pattern, let's explore